Hi everyone, today I'm going to talk about how to pet bugs. So BUGS is Bayesian inference using Gibbs sampling. It is a computing language to specify statistical models, for example, prior and likelihood. And once we specify those, we can generate samples from posterior distribution. This talk will be divided in 4 sections. In the first section, I will talk about bug syntax. Then I will talk about various available bugs engines. Then in the third section, I will talk about bugs interfaces. In the fourth section, I will talk about various softwares that could be integrated with bugs. So let's talk about core syntax that are required to run bugs. At first, let's define the variable types. There are two types of variables. The first one is deterministic, and by nodes I mean variables, and the second one is random. When we define a deterministic node, we define it using a less than and hyphen sign, whereas when we define a random node, we define it with a tilde sign. And you can see there are various distributions that are supported by bugs, and we can generate samples from those distributions when we specify the parameters. For example, it supports Bernoulli, binomial, Poisson, beta, exponential, gamma, normal, uniform, and many other distributions. So after we talked about variables, let's move on to what other functions it supports. There are functions such as absolute values of x, cos, whether x and y are equal or not, exp, log, logit, rank, round, sine, square root, and sum. In terms of statistical function, we can see maximum, minimum, mean, step function, standard deviation, C log log, and ranked. We can find the order statistic using this ranked function. For example, we could find the minimum and maximum using this ranked function as well. Now, how can we use the parenthesis? So we can see the first bracket or the parenthesis is can be used by the functions and expression. The third bracket can be used by to specify the element indexing. The second bracket can be used to specify the loop and the model specification. We can use not available or NA to indicate missing value, and also we can use hash for commenting. Now, to define a vector, we can specify v, and within third bracket we can have nothing to specify that this is a vector. And if we write v and within third bracket if we write I, that means we are calling the ith element of that vector. Nesting is possible. And we can see to define a matrix, we write M, and then within third bracket we give a comma to specify that there are rows and columns. Similarly, if we write M within third brackets I comma, that means I'm calling the ith row, and similarly when we write comma j, we mean the jth column. And similarly we can expand it to arrays with multiple dimensions. Now, to do the looping, it's the for I in 1 to n, and then the curly bracket starts, and within that you can define the random node or the deterministic node, whichever is required. And nesting is also possible within the loops. And to define the multivariate distributions, you can do it using the same way as doing looping, but these bugs do not work vector wise, it works element wise. So you have to specify the elements as well and the index of the elements as well. Just like looping, when we were dealing with just one element, and now we are dealing with multiple element because we have specified the index of it. Now you can see this syntax uh, has high resemblance with R or S+. So what are the differences between S+ or R versus bugs? So the first one is that the order is not important because everything is compiled simultaneously. You do not have to define something first and use it later. You can define it in whichever order you want. And now for math functions, they work element wise as I have mentioned. And in R, when you define a vector v, you do not have to specify the third bracket. But here you have to specify the third bracket when you are talking about a vector matrix or an array. And here matrices are filled row wise, and um, in R we usually define a vector before filling it up within a loop. But here we do not need that. We can define a vector within a loop without even defining it first. Alright. To construct the model, for example, to construct the likelihood, we can simply use the for loop to generate the whole likelihood, and also same thing is true for priors. And to import data, there are two ways. The first way would be to write the data in this way, so that all the variables are column wise, and at the end of it there is an end. And the other way would be to writing a list. For example, we write lists in R. This is something similar. We could write a list and define all the variables within there. For example, here I'm defining x bar n t x y, and within y there is a matrix with 4 rows and 5 columns. And this is how we can write data or import data in WinBUGS. So we just talked about the core syntax. Now we'll move to the next section. It's called available engines. So the first engine was developed in 1990, and the project initiated in 89, and it required us to define a couple of things. For example, it required us to define preamble, define the constant and the variables. Then it required us to define data model and initial values. The next engine is the WinBUGS. So you can see this is the WinBUGS website, and to download and install WinBUGS you download this exe file. But if you are working on a 64-bit machine, you should download the zip version of the file and then extract it in your hard drive and click on the WinBUGS icon, and then you see WinBUGS 1.4 interface like this. But you can upgrade it to 1.4.3 by getting the patch from here, and also you can use this software for free by getting the license keys. The license keys look like this. The first one is for updating, and the second one is for using it forever. You can download them and open them in your WinBUGS, and from your WinBUGS go to tools and then decode, and from decode you select decode all. Then you can use WinBUGS forever. And this WinBUGS, compared to the classic bugs, the difference is that you do not need to define the preamble here. You can straightforwardly define data model and initial values and go on with it. You do not need to define the preamble. The next engine is the OpenBUGS. It's the open source version of the WinBUGS. The WinBUGS was free, but it was not open source. But OpenBUGS is an open source version of it, and when you download it and install it, the interface sort of looks like WinBUGS, and it runs on Linux as well. So the next version is JAGS. So by JAGS we mean just another GIF sampler, and when we download it, we can download it from the source port, and when we install it, it sort of looks like this. And now we have discussed about 4 available engines: classic bugs, WinBUGS, OpenBUGS, and JAGS. So we know about the engines now. Next, if you need some support, there is a mailing list. It's called bugs at diskmail.ac.uk. You can join there and post your question or follow the questions that are posted there. If you want to contribute to the bugs development, there is a bugs developers mailing list. You could join there as well. Now let's move on to the next section, the third section. It's called the bugs interfaces. There are three type of bugs interfaces. First one is GUI, second one is scripting, and third one is doodles. Let's go to see how the GUI works. So at first, open the OpenBUGS. It will also work on the WinBUGS because the interface of WinBUGS and OpenBUGS are almost the same. And the example we are going to show here is the example that is provided in the help and examples volume 1. And we are going for the first example. It's called the RAS, normal hierarchical model. And from here you will get the description of the problem that was discussed here. So to run this problem, we first select the models and then put it as a script in here, where we can see there are 3 scripts here. The first one is for model, second one is for the data, and the third one is for defining the initials. So there are 3 steps to define. First we will define the model. To define the model, we will select the model and then specification, and then we will get a new pop-up window. In that pop-up window we will see there is a button called check model. Before selecting check model, you should highlight the model part of your script and then press check model, and in the status bar you will see it says model is syntactically correct. Then in the second section, what you have to do is that you have to define the data. So the data that was defined or given in the example, you can write it in a list format and select the list word and then press the load data. You will see in the status bar it will say data loaded. So now press compile. In the status bar it will say model compiled. And in the third section, what you have to do is that in the same pop-up window you will see a button called load inits. So you write all the initial values in a list format again. Now select the list and then press load inits. And if you need to define more initial values, list them as well, or if you need to give another set of initial values, select the list and then press load inits. And after doing that, you will see in the status bar it will say model is initialized. So after model is initialized, now you will sample from the posterior distribution. So go to inference samples. It will give a pop-up window like this. Now you have to give the nodes or which parameters you want to monitor. So there were 3 parameters: alpha 0, beta.c, and sigma. Write each of these parameters name and click set three times. uh, First time when you write alpha 0, press set, then you write beta.c, then press set, and now write sigma, then press set. And if you want to monitor them all, write static. Now if you want to update the model, go to model and then update. You will get a pop-up window, it's called update tools. Now press update there, and you will see all the uh, models that you have inserted, those will be updated. So we go back to, after updating the model, we will go back to the sample monitor tool, and in the sample monitor tool you can get various statistics, coda, density, trace, history. So just click them all, and when you click all the buttons, you will get something like this, where you will see the trace, the codas, the statistics, autocorrelation, history, running quantiles, acceptance rates, all of them. So this was the GUI format. So you had to go through a lot of clicking and selecting and all that. But usually statisticians don't like to select a lot of menu based clickers and all that. So we go to scripting, and you can see just by writing couple of lines you can avoid all these GUI steps. You can simply write all this scripting and you can run the models, and you will get the same values that you got here. All the plots, all the statistics, you will get all of them at the same time. You do not have to wait. And the advantage of this is that this is automatic and portable and obviously reproducible. And if you want to change just one thing, you can just change that one line. Say for example, if you want to update 3000 times instead of 1000, you can simply delete one and write 3 over there and run the whole thing, and then you will get your desired results. Whereas when you were using the GUI, then you had to go through all the steps all over again. The next step, or the next interface, is doodles. This is basically for non-programmers who are not comfortable with writing programs, and instead of writing the models in the way that is written here, you could simply use your doodles menu to write a model like this by just selecting and clicking and renaming some stuff, and it will generate a model like this at the end. Basically, if you are familiar with programming languages, you probably need this, but for many social scientists who are not comfortable with programming, they probably can use it. So we talked about the bugs interfaces. Now we'll move on to the last part of the talk. It's called the bugs integration with other softwares. So at first we'll talk about R. There is a package, it's called R2 WinBUGS, where in the usual way you can define all the data and you can put all the data in a list format. And once this is the first step, in the second step you have to define the parameters and then select the initial values of those parameters. This is the second step. And in the third step, we set a working directory, and within that working directory we write a function which includes the model, the likelihood and the prior, and we write it in your hard disk in the working directory, and then we can see the model from there, or we can read the model from WinBUGS. Now once we have done all these three steps, we have included the data in R, we have selected the initial values, and we have written the model in your hard disk, then we can use the function called bugs. This is a function in the package R2 WinBUGS. and we can select the number of chain, number of iteration, number of burn-in, how thin it should be, and we have to specify the directory where the WinBUGS is installed. And then you can see after running the bugs program, WinBUGS will pop up. It will do all the calculation and it will go away if you select debug equals false, and then it will give you the results of that run. But if you want your WinBUG to run even after running this, you have to write debug equals true, then the WinBUG will not close. So the second package I'm talking about is the BUGS. BUGS can be used to run the same thing, but this time it's in OpenBUGS, not in WinBUGS anymore. You could do it using the bugs, where you can specify the program equals OpenBUGS, or you could directly use OpenBUGS function to get your OpenBUGS working. The last one is JAGS. This is the same thing. It uses the JAGS instead of OpenBUGS or WinBUGS, and the function's name is JAGS, where you define the data initial value and the model, and then you update. After doing that, you can get your samples, and once you get your samples, you can use the CODA or BOA package to do your diagnosis after you have collected the samples. For example, you could get the trace plot and the density plots all together or separately, or you could get the autocorrelation, cumulative plot, cross correlation, GUI plot. This is a diagnostic plot, and also the Gell-Mann plot from the Gell-Mann and Rubin diagnostics. So that was R. Now in SAS, you could either do it using, there are two macros at least available that can connect bugs and SAS, or you could use it remotely. To get more information about that, you should go to WinBUGS website, and that gives you the whole code of how to do this. So in Stata, there is a package, it's called BUGS.dat. It can convert the selected variables in BUGS readable format. BUGS-util package, what it does is it imports and exports the stats or the codas into Stata. BUGS-write writes the data values to screen in a WinBUGS readable format. Probably the most important of all would be the WinBUGS from Stata package, which can be downloaded from this website that is listed here, and from there you can see you can run the MCMC from Stata using WinBUGS in the background, and you can generate a lot of plots and diagnostic statistics from this. The next one is MATLAB. This is something that was developed by Kevin Murphy, and RAS example that I have shown you before, it sort of looks like this when you run it from MATLAB, and the software's name is MATBUGS, and the code is like this. Alright, we still have two other softwares. One is GenStat. There is a function, it's called BGX GenStat procedure, that can use WinBUGS from the GenStat. And also there is another the program that can use it. It's called BUGS XLA, and that can integrate Excel with BUGS. And this is the book where you can get all the instructions of how to do that. So we have learned about how to integrate other softwares into BUGS. So basically what BUGS do is BUGS collect the samples from the posterior, and you can do your post analysis using all these softwares if you are comfortable with these softwares more than BUGS. So we learned about the integration. And if you want to learn more about how to use bugs or WinBUGS or OpenBUGS or JAGS, there are a couple of books that could help you. The first one is the Bugs book. It's written by the uh, authors that actually wrote the bugs in the first place. And this is a new one, and there are some other books. For example, the book Bayesian modeling using WinBUGS is a good one, and then there are very topic specific books. For example, disease mapping with WinBUGS and MLWin. And for ecologists there is a book, it's called Introduction to WinBUGS for Ecologists. And from the same author and another co-author, there is another new book, it's called Bayesian population analysis using WinBUGS. You could read all those books, or you could go to the WinBUGS website or the OpenBUGS website, and all the manuals are free. You could see those examples and try to learn WinBUGS or OpenBUGS or any other bugs implementations. Thank you for listening.